to computer engineering. This is something that is kind of cool and interesting. So we were just talking about why Google would special design and build their own chips to do what they call a deep neural network computing, and it's only because they want to save money. Okay, they want to save money because otherwise they would have to build new data centers, multiple new data centers to accomplish the same type of computation power. By building these neural network chips, they can now reuse existing equipment, existing facilities, and without having to spend a lot of energy. And for those of you who don't know, Google registered itself as an energy provider. In other words, Google as a company is licensed to have its own generators and sell power. But Google actually had no intention of selling power or making money out of selling power. It only wanted that license so that it can have its own power plant to power up its own data centers. That's how much energy it is consuming. Okay, instead of buying power from SMUD, buying power from PG&E, they want to say, oh, we want to save money. We want to have our own nuclear generator sitting next to the campus. Well, not really next to, but but they want to have their own generator because this way they can operate with a lower budget. Okay, so they're really doing this to save energy, to save facilities and whatnot. The reason why I brought this up is neural network chips is a kind of ASIC, ASIC, which stands for Application Specific Integrated Circuit. Okay, and it's not a new idea whatsoever. It has been around for a long, long time. But people have found that companies have increasingly used or designed their own ASICs these days for huge data processing demands like neural network processing. And you might ask, okay, one, how does this relate to my daily life? And two, how does it relate to this class, right? Okay, perfect questions to ask. The first one can be answered every time you use your speech recognition feature, whether it's Siri or whether it's Google Speech or Google Voice, okay, or using the automated closed captioning of YouTube. Those are all done through neural networks. Okay, so that's how it connects to your daily life. How it connects to this class has to do with what type of computation are they doing with these chips? They're really just all the simple stuff that we do. Okay, adding, multiplication, that sort of thing. Okay, but they're designing the processor so that they can have multiple calculations going on at exactly the same time in the same chip. You're talking about, okay, what is the newest AMD processor? How many cores does it have? Is it called the Ryzen processor?
It's Ryzen 7. Oh my God.
Ryzen 7 has 17 cores.
8 cores?
Has 8 cores, okay, and how many threads can they track at the same time?
I think it says 16.
16? Okay, so it can track 16 threads at the same time. These days can track multiple hundreds, if not thousands, of calculations at exactly the same time. Your GPU can do that too. Okay, how many of you are gamers? You don't have to raise your hand if you don't want to. Okay, so when you buy that $500 graphics card that has its own cable to connect to it straight from the power supply, how many processors do you think it has? How many things can you do at the same time? Hundreds at least. Okay, and that's because when you look at computer graphics, it really lends itself to parallel processing. Why do you think that is the case? How is an image rendered in the game? It's through what we call ray tracing, okay, or at least a variation of that technique. So ray tracing is actually pretty easy, very simple idea. So what you do is you look at your screen. So let's just say that I have a really, really crude screen that has only 20 pixels, okay, 20 pixel screen, easy. So what they do is they have a imaginary location that you'll be sitting at, and then they say, okay, you're looking at the screen, and then when your eye, they look at the line that is passing through the first pixel, and then they look at the quote-unquote world, the objects that is in the virtual world, and they say, okay, if I just follow that line of ray, okay, reverse ray, so to speak, because it's actually coming out, but you can track the line backwards too, right? So we would track it backward and say, okay, what is the first object it's going to hit? Oh, it's going to be the surface of this kind of chrome shiny object. Then we'll do the reflection, right? Then we'll ask, okay, what else is going to hit? What else is it gonna hit? What else is it gonna hit? And it will do these computations until it gets to a light source. Then it will go like, oh, okay, this color or this pixel should be blah 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 color. What do you think it's gonna do to the next pixel? Exactly the same thing, exactly the same thing, exactly the same thing, and so on. So as long as the objects are represented in every single code processor exactly the same way, all of these calculations can be done at exactly the same time. Because there's no interdependency between the pixels or the calculations of the pixels. Does that make any sense? So your GPU is basically making use of this fact so that it can just throw many processors at the problem, and it is scalable. If you throw twice as many processors into your GPU, then you will be able to compute it twice as fast. There was a question?
It's kind of random. So I think I've seen before where if you have a lower powered graphics card on a monitor that's too high resolution, you actually see the line going on the screen. Is that related to this?
It is related, but you may not see that because what happens is the rendering can be happening in the background. So it is using a different portion of the RAM of your computer to do all the rendering. When it's done, then it will switch what is originally rendering to the background, and then it will switch what is already rendered onto the screen. So it depends on the game engine, to see whether it is updating what you're actually seeing or whether it's updating something in the back and switching in. Yep. So that's basically how frame rate is affected by your GPU, because the more processing units you can throw at the problem, then the faster the refresh, because now instead of having only like 16 processors to do all the pixels, now you have like 64. So it's 4 times as fast. Which is kind of cool because the same architecture, your GPU is also quote unquote abused by these people at Google and what other company, and they use that for neural net computations as well, because neural network computations is also easily parallelized, and that's why they can also use GPUs for that purpose. But they found that GPUs are not even a really good fit for neural network computation, and that's why they designed their own chips to do it. So this is an interesting article because a lot of the stuff that we talked about in this class, like the registers, the ALU, all the computations, and how we control the pathways. People who design the neural net, chips, people who design the GPUs, they all have to understand exactly the same thing too, because when you boil a GPU all the way down to its components, those are all muxes and adders, subtractors, and the same kind of elements that we see in this class. Yep.
So with server CPUs, those use parallel computing also, right? They have to hold a lot of threads so they can host like multiple servers?
Yes.
Is that why they do that?
Yep.
Okay.
But that's different. Those are not special purpose. Those are general purpose.
CPUs just have a lot of threads.
Yeah.
Okay.
So they can do a lot of general purpose stuff and also special purpose stuff. But for all the special purpose stuff, they're inefficient. So you have to go through a lot more overhead to get the same computation done, as opposed to the specialized chips that can just get all that specialized things done with little energy spent to do the housekeeping stuff. Because your general processor, like your Intel processor or your AMD processor, is a general purpose processor. So it's designed to handle a variety of things, and because of that, when you just want to do neural net computation, it's not very efficient at doing that. All right, so it's just something I want to kind of bring up because I think it has some relevancy to this class, especially what you might want to do when you graduate, from a 4-year university. Okay, so let's go to 310. And the demand of ASIC chips and also neural network chips is going to be increasing. And you can only imagine what kind of application it can find itself into. Right now, we only find these in big, huge data centers like Google, because they have to do all these voice recognition, image recognition, and stuff like that. Think about self-driving cars. Okay? How would you apply a neural network chip in self-driving cars?
Sort of machine learning so that they adapt to circumstances on the road that they've seen before.
Yep, like figuring out that the driver in front of you or across on the other side is drunk. Okay, if your vehicle has an ability to detect signs of something that's potentially dangerous before it is posing actual danger to you, it's better, right? At least your vehicle will say, okay, I've got to slow down or stay away from that car, increase the distance to the car in front of you, or something along that line. And the training data is coming from actual observations. You can pay someone to get drunk and drive and collect data. Yep.
So do self-driving cars use GPUs because of the ray tracing thing? Is that what they do when they're like the sensors are looking for other cars? Is it sort of like ray tracing except?
It is kind of like a reverse ray tracing. It's called LiDAR, LIDAR,
Okay.
which is laser, infrared, and then what is DAR? I cannot remember, but it's based on time of flight. Okay, so what's happening is it has the current generation. I think they still use a scanning mechanism.
Yeah.
So they basically shoot out a very short pulse of infrared energy, a very short pulse, and then they measure the time of the emission and the time it bounces back, and then it uses the time of flight to calculate the distance between. Yep. But they're working on a non-spinning ones, like solid-state type of chips that can do the same thing, which is based on the same technology in the projectors. The DSP, or not DSP, it's called DLP chips. So they use a semiconductor to actuate tiny little mirrors on the chip to change the angle of reflection. And then they're using that to implement the next generation of LiDARs. Because LiDARs are very expensive right now. They are at least in the $1,000 range of dollars. And that's why self-driving cars are going to be expensive for a while until the technology like LiDARs and whatnot, they'll get to the sub $100 range. Then we're looking at mass-produced self-driving cars. Yep.
What does Tesla use?
I do not know. Probably a hybrid of technology, but they need LiDAR in order to detect pedestrians, signs, and other objects. All the code base of self-driving cars probably can trace back to Google and possibly Stanford University, because those are the organizations who first came up with the framework of self-driving cars. So Uber stole some of that stuff. And that's why they're in pretty hot water right now. Just look it up. Look up, Uber.
Yeah, I got it.
Yeah.
Could they create an ASIC for self-driving cars instead of using GPUs at one point?
It depends on the cost effectiveness, because the R&D of an ASIC can be significant.
Okay.
So it depends on how many cars they plan to sell within a certain amount of time before the chip is obsoleted. If it's worth it, then they will do it. If it's not, they might just kind of fall back on general purpose processors. If they find a separate use of those chips in different applications, then they might use an ASIC too. All right, so we are looking at the practice exam and talk about the solution to the sample questions. All right, so question number 1 is to ask, using the current, not correct, is using the current architecture, if a program needs to increment the value of a single register, let's say register A, what instructions do we need to use? Okay, this is a fairly easy question because we have already talked about most of those instructions already at this point. So I'm using a text editor to enter the answer because there's no need to handwrite anything at this point. Okay, so to answer question number 1, it is just an LDI. You just pick some register B, C, or D. Pick one of those, and then you just say add AB. Okay, that's the answer of question number 1. Is that okay? All right. Okay. So we can do it. Question number 2 is, with your chosen sequence of instructions, what is affected other than the register that we are incrementing? Well, that's pretty easy. Okay, register B is also changed because register B may have some values other than 1 before. By changing it to 1, now register B has changed its value. But there's one more register that is also changed. Okay? So when you look at the architecture, so this would be a good time to start up the startup Logic Sim, and make sure that we are streaming and also the audio is on. Okay, just double checking. Okay, so this is a good time to start up the simulator, which is Java, jar, Windows, Logic Sim, generic, processor with direct PC access. There we go. All right. So when you look at the ALU, okay, the ALU itself has no register, so you can everything is transient to the ALU, so it's not a problem. But we have the flags register. Every time you enable the ALU, you're also enabling the flags register. So every time you do any calculation, add, subtract, compare, bit shift, or anything like that, it is also changing the flags register. So the way that our instruction is designed will also change the flag register. So the correct answer or the complete answer is the flags register is modified, potentially modified. I think everybody got the register B or the other register part, but I'm guessing not too many people got the flags one.
Would we say also the ALU was enabled, or do we not mention that?
Well, you don't have to mention that because I'm just asking which part is affected.
Okay.
So in terms of which part is affected, the flags register is affected. Yep.
And also the PC counter.
The program counter, right? The program counter is always going to be affected, so it's not as much of a problem, but definitely PC is incremented. Okay. All right, those are all good answers, but the flags is a problem. Okay, later on we'll see why that can be a problem. Okay, are there any questions about number 2, which is based on number 1? Yes?
So we don't have to say what they're modified to, like we don't have to say what's going to be in the flags register?
Yeah, we just have to say, because we don't know. Because we don't know, whether the addition ends up in a 0, where the Z flag is going to be set, or whether it's going to cross the line between the highest value of a signed number to all the way to the negative side, in which case the overflow flag is going to be set, right? So we don't know, the exact transition that might happen, so we cannot tell how the flags register is affected. We just know that there's a potential that it can be affected. There's no guarantee that it can maintain its old value from before. That's the best way to put it. All right. So are there any questions about number 2? So number 1 and number 2 is really guiding you to the other 2 questions, number 3 and number 4. So let's go to question number 3. Okay, number 3 is kind of tricky. Well, I wouldn't say tricky, but it takes a little bit more time to think about it and to derive the answer. Reviewing the processor architecture right now, how would you propose to connect the data port of RAM to in2 of the ALU? This is so that we can allow instructions to directly use RAM content out of the data bus as the second operand of arithmetic instructions. Your suggested change should not affect the microcode of current instructions, nor to introduce additional control lines. So that's the trick, okay? You have to basically look at all the instructions right now and go like, okay, how are those going to use the various lines of the processor, and how this new instruction, how can we design the processor so that we have a new way to connect the data port from RAM directly into the in port of the ALU, but without introducing problems. So in order to do that, you probably have to spend some time to kind of look at and examine this circuit diagram. And one way that you can probably do when you're using a computer, can't do that during the exam because it's going to be paper-based. But if you look at this design kind of enough times, you start to recognize how certain components are connected. So when you click on the D, the data port, it will highlight everywhere that it goes to. Okay. So we somehow want to connect what is already highlighted in the projector to in2 of the ALU, which is right here. But we want to make sure that all the current instructions do not get messed up. Okay. All right. So what do you think? Now, one thing you can borrow is how I modified the architecture to lay down a new path from the data port to the input of the program counter.
You had a OR gate?
Hmm?
You had an OR gate?
You have to add, yes, in this case you did an OR gate, but you need some kind of gate to control a mux, okay? So the key is a mux first, okay? So whenever you're connecting, you're trying to put another line to connect to something that already has a current connection, you're either looking at a mux or you're looking at some leftover slot of a mux that is not fully utilized. I can point out which ones are not fully utilized. In terms of mux, I don't think we have one that is not fully utilized, but in terms of demux, we have one line here that is not utilized. But it's not going to help us in this case, okay? Because this is controlling the output of the register bank, it is not controlling the data port itself. So it's not going to help us. But what you need to do, or what you can do in this case, is to think about what I did in order to bring the data port to the program counter. Do you guys remember that part? Okay, so let me bring up bring up the original processor design first, because from the comparison of those two, let's see if we can use that to help us derive this circuitry. So we'll open up the one that is before the modification. This is the one before the modification. And let me just go ahead and line up everything so that we can focus on just the part that we want to look at. Okay. Let me magnify a little bit so that we can just focus on that one little thing. And I think they're pretty close now. This is before, and this one is after. Okay, what is the main difference? Let me see if I can do this. Let me see if I can just show these side by side. Just give me a second to set this up. Resize this one. Yep, that will work. And we'll scroll it just to the right place, right about there. And then we look at the other one, do the same thing. So this way we can look at these two, kind of not exactly side by side, but top and bottom. There we go. Okay. So this gives you an idea of what I did, or what is the modification. What is the main difference between these two circuits? Exactly, we have one new component, which is the mux, okay? So that's the first thing you need to think about is, okay, we have a new way of connecting something to something that already has a connection. So we need a switch. We need a switch to choose, oh, do I want the usual way or do I want the new way? You need a switch, you need a mux. Is that okay? So that's my line of thinking. Okay, when I design the circuit, this is the first thing that occurred to me is, okay, I need to be able to choose. Okay, normally we'll go in the old way, but in some newer instructions, I want to go with the new way. Is that okay? And every time you introduce a mux, you're having a way to go from one input to multiple outputs, or go from multiple input to one single input. So you need a way to choose. Just because you have a mechanism to take multiple inputs to have one single output is not done yet. Okay, you have to find a way to choose. So once we add a mux, which is this guy here, then we have to worry about this line here. It's like, okay, how are we going to choose? Okay, so now the difficult part is to figure out, okay, what are the signals that we can rely on to make this switch? And how do we combine those signals? Is that okay? So I'm going to write down my line of reasoning first, just so that there's a reference of how my mind works. Doesn't necessarily mean that yours is going to work the same way. Most likely it's not. Okay. So when we need to make a new connection to something that is already connected, we need some kind of switching mechanism. Oh, there we go. Is that making any sense? Okay. Mux is for multi-input single output. Demux is the other way around, is for multi-output single input. So depending on what we are trying to accomplish, are we splitting something into multiple potential outputs, or are we merging multiple inputs into one single output? That's what you need to do, is to figure out, okay, do we need a mux or do we need a demux? In this case, we need a mux because we need to have a way to bring multiple inputs to one single input. So the mechanism needs to have multiple input and one single output, and that's why we need a mux in this case. Okay. So once you identify the unit mux, then you probably will figure out where one end of that mux is going to connect to, right? So that part is easy. Okay. So once you figure out whether you need mux or demux, so now the next step is to connect the mux to the related signals or traces or lines, however you want to call that. Okay. That's not the difficult part. The difficult part is to specify how the mux is controlled. In other words, when is the mux going to choose this as the input? When is it going to choose that as the input? That is the most difficult part. Are we doing okay so far with the rationale? Okay. All right, so keeping this rationale on the board, we are now going to take out this screen because it is no longer needed. So what we'll do is we'll use this screen, zoom out a little bit so I can find out where we are dealing with. So now we are dealing with the ALU, which is this one here, and we want to connect the data bus to into of this thing. So I'm going to zoom in again, just so that this part is shown better here. And the data line is this one. Yep, there we go. So we want to connect the data line somehow to into, but into already has an input, which is the output of this demux here. So we need a way to choose. So getting back to the rationale, which is explaining how I work on this problem step by step. I already had the right solution, but obviously I forgot about the solution already. Once I worked it out, I forget. Okay, so I'm just working on it with you right now at this point. Okay, there might be some faint remembrance somewhere of the actual solution, but I actually do not have exact remembrance or recall of that solution. Okay, so now we have to say that the demux or the mux output connects to into. Is that making any sense? Because after all, we want to bring that new line, which is the data line, into. So that's fine. Okay. One mux input connects to the current way of doing things, which is let me see the destination here. So the current way of connecting is out one from this particular demux here. So one mux input connects to out one of demux of I think that's register bank output one output. Okay, pretty sure about that. Yep, there we go. So that part is okay. That part is pretty easy. And then the other mux input connects to what we want. This is actually what we want to do, which is the new way of connecting to the into of the ALU, which is the data port of RAM. Okay, are we still doing okay so far as the rationale is concerned? I'm typing this out there just so that we can look at it and you guys can ask questions about it, and it's also a part of the recording. Okay, so now the remaining portion is how do we choose which one and what we can include to do it. So in order to get an insight of this, we can look back to the design of the PC first. Okay, so we go back to the PC mux and we say, okay, so we use PC mux and RO0EN in this case, and we use an AND gate in this case to say, okay, let's these two together, one is negated, the other one is not. But when we use an AND gate, we say PC mux and not RO0EN will turn on the mux to 1, which is connecting to the data path. But why would I do that?
Maybe when they're both on, there's some other,
Hmm?
well, when they're both on, maybe there's some other, action assigned to that.
Right, because because the PC is already connected to the input of the PC is already connected to the output 0 of the register bank, so that we can do the regular jump, the regular conditional branch instructions, right? Okay, so getting back to the rationale here, okay, so getting back to the PC problem, okay, the PC is connected to, okay, I have to use past tense here, was connected to register bank output 0, excuse me, this is register bank output 0, okay, for JMP instructions. Okay, JMP, all the other branch instructions, JZ, JC, JO, JS, JL, all of these instructions require that path because we are using a single register in the register bank to update the program counter, and that's why we have the original path. So we want an alternate path in this case, which means, oh, we're not using a register, we want to use whatever is in RAM to do it. So that's why, RO0EN is a part of the equation because it is one of the most important component here, because it say by negating that, it means if I'm dealing with the normal JMP instructions, which will turn on RO0EN, it will automatically turn off quote unquote the AND gate will output a 0. But when the AND gate is outputting a 0, I'm just going back to the default path what we used to do, which is okay. So all the existing instructions, the JMP, JZ, JC, all of those instructions, they will still work. Is that okay? And then the negation of that is basically saying, oh, if I specify something just like the JMP instruction, but I do not enable RO0, output 0 of the register bank, then it will choose the other one. And I have another one which is PC mux here, just to make sure that I do not, just to make sure that these two are conditions together to enable that program, to enable this path to the program counter. But the line of reasoning is like that. Okay, we have to look at all the existing instructions and how this connection is used. And then we say, oh, but now that we want a different way of using these instructions, what can possibly be used to help me make that decision? There's one more, okay? There's one more circuitry change that I did, which is this part here. This is the change that I made while the homework assignment was already assigned, and I said, oh, by the way, it's flawed because there's no way to actually continue execution because there's no circuitry to auto increment. So that's the other one that I added in order to say, oh, if PC inc is a 1, go ahead and increment. But on the other hand, if address mux is a 1, also specify the increment, because in that case, that is going to be turned on with our new instruction. Okay. So these are the reasons, these are the rationale of how I modified the processor up to this point. So now that we have a new problem, a new connection, we need to find a new way to make that switch work. We just have to think about, okay, what is the existing way of using this connection? What instructions currently use this field connection? All of the stuff that needs calculations, right? So we have all the instructions, so let me write down here. Okay, so the next question is, what current instructions use the connection between out one of the demux? Okay, I'm just going to use demux here. Is that okay? Okay, between out one of demux and into of ALU. So we have to kind of think about, okay, what instructions currently use this connection? We have a pretty good idea of what instructions. The AND instruction, the OR instruction, the add instruction, subtract, compare, bit shift or right shift. I think these are all the the 6 instructions. Okay, all of these make use of the ALU. Now remember, in the test, it is open book, open notes. You can bring anything to help you in the test. So what do you think what are you gonna bring in order to look up and say, okay, what current instructions make use of the ALU? Sorry?
The assembly instruction opcode list.
Yep, the opcode list. Okay, so you can bring all the listing of add.c, subtract.c, compare.c. You can bring those source files with you. Now, if you say, well, but all of those look about the same, you can just compile your own table. Compile your own table, label the columns, and then populate the entire table. So you have one centralized place to look at. This is instruction. This is what is in the microcode. The second slice is always just resetting the microcode pointer. So that one you don't really have to capture because they all look pretty much the same. So you just have to capture the first line, make your own table, so you can look up very quickly. Just look up, in this case, look up ALUEN, because you need ALUEN to be a 1 in order to use the ALU. Look up that column. Whatever has a 1 over there, look up the rows and find out, oh, all of these are the instructions that will make use of the ALU. Yep.
Have you released solutions to the homework? Like, have you really coded that?
Not yet. So today would be a good day to work on that too. Yeah.
Okay.
So, but it's about the same kind of reasoning.
Sure.
You have to kind of exercise the same type of reasoning to get this done as well as the homework. So I will get to the homework too. But good reminding. So now we know that these are the instructions. Then you have to ask, what is common amongst all of these instructions? Now, when you think about what is common among these instructions, you can think in terms of the positive ones, like, oh, they all use registers. But you can also think about the negated reasoning, which is, what do they not use? None of these use la 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 la. Okay, so you have to kind of identify that pattern. And then you start to go like, oh, maybe we can use that as a clue. So the second thing you have to do is to think about the new instruction. So when you look at the new instruction, okay, look at the question itself. In Q3, it asks that we want to allow instructions to directly use RAM content as the second operand. Okay, so we have seen this picture a lot already. Okay, but in order for the data line, which is this one here, to have any meaning, what lines do you think have to be actuated as well? This is the data output of RAM. Yes?
RAM load.
RAM load and RAM select. Okay? Very good. Okay. So that means we have some clues here. And if you read the instructions or the question here, so if I want an instruction to directly use RAM content as the second operand, how do you think I'm going to specify that location? This is a part of question number 4. So question number 4 says you're borrowing the idea from the LDI instruction. So the LDI instruction uses a RAM location to specify the content to put into a single register. But how do I specify that location in an LDI instruction?
Next byte in RAM. It's next byte in RAM.
The next byte in RAM, but what is driving the address bus so that, oh, hey, you RAM, I need that location. The PC. Okay, very good. So the PC is another piece of this puzzle. Okay. So now that we can, okay, so if I am working on this problem, I'll probably have like a scratch paper to put all of these things here. So we know the PC is involved. We know RAM is involved. But if RAM is involved, we also know that RAM LD is involved because it's a read operation. We know RAM cell is involved because we have to select or activate the RAM module. So we know all of these things are important. Is that okay? So I'm just throwing everything that I think is important into a bin first. And then I try to figure out, okay, how do I make use of these things to help me decide this? Is that okay? Okay. So in order to use that D, to make that connection, I know RAM load is going to be important. Because without RAM load, I wouldn't be reading from RAM. which means the data line would not be driven by RAM, which means, hey, it just defeats the whole purpose. So RAM load is one of the things that I can rely on. So if you have one thing that you think you might be able to rely on, let's try that first. Okay? If it doesn't work, then we'll figure out something else. So we'll use RAM load by itself and say, can we use RAM load to make that switch? Okay, so try to use RAM load to select the inputs of the new mux and see if it works. Okay. Now obviously, because this is a paper test, you cannot really run it through the simulator, but you can kind of just simulate it and go like, okay, if RAM load is a 1, would this mux work? Okay. So if I use RAM load by itself, okay, so the new connection is like this. Okay. So as far as the new mux is concerned, this is how we are going to connect it. In 0 of the new mux is connecting to the demux, the current demux out of register output 0, RO0, output 0 of the register bank. In 1 is going to be the data port out of RAM. The output of this multiplexer is going into in2. And the selection is going to be just RAM load itself. So the selection of the multiplexer is RAM load. Okay. So this is what I'm proposing. Maybe this works, maybe it doesn't work. So we have to go through all the existing instructions first and see whether this will work with all the existing instructions. All the existing instructions, like add, subtract, and multiple, so on. Oh, okay. No problem. My deep neural net is not working. It's false positive is what they call the false positive. So we have to look at all the existing instructions, which I have listed earlier. So all of those only want to use registers. None of those instructions want RAM load or RAM cell to be a 1. Okay, you can look at the table, you can find out, hey, they don't use RAM at all. So this modification will not modify the behavior of those existing instructions, which is important. So the new question is it going to work with the new instructions? So you have to look at question 4 now. So question 4 is saying, okay, I need something like this, where the effect of add I or add immediate xi is register x is going to be incremented by whatever content is pointed to by the program counter. And the program counter needs to be incremented after this, okay? So you look back at the circuit here and go like, would that work? In other words, would I be able to select a location in RAM using the program counter and use the content of that location as into once we have this modification? And the answer is yes, okay? There are many other lines that we have to modify, other places we have to modify as far as the microcode is concerned, but this will suffice as the switch. Okay? So, but to answer question number 4, you have to basically come up with a table. In the exam, I will give you a table, where all the fields are listed, and you just have to enter, okay, this is going to be 1, this is going to be 0, and so on. Okay? But for the purpose of this demonstration, I'm going to use, I'm going to cheat a little bit so I don't have to type everything. And instead I'm going to go to my opcodes folder. And I'm going to look at ucode.c, and we're just going to go through these items one by one and say, okay, if I'm talking about the first slice of the add I instruction, which one is going to be 1, which one is going to be 0, and so on. Okay. We'll go one by one, and I just have to remember not to save this file. Do we want a microcode pointer reset as the first slice of this instruction? Yeah, probably not, right? What about microcode pointer select? In other words, how are we updating the microcode pointer? Okay, let's go back to this one, zoom out. And since you can refer to existing instructions, do you think this instruction is different from all the other instructions as far as the microcode pointer is concerned? Nope. There's only one instruction that is kind of awkward as far as the microcode pointer is concerned. The hold instruction. That's the only one that has a really special trick with the microcode pointer. All the other ones have about the same type of control. So you can just copy that. Or if you want to work it out again, you can just go to the microcode pointer down here and say, okay, how do I want this mux to be? In other words, how do I want to update the microcode pointer? We probably want to use the adder to update it. And that's going to be using path 1, which means this is going to be a 1. Microcode pointer select is going to be a 1. What about PCEN? There are two ways to do it. Okay, if you want to play it really safe, you can actually not turn on program counter enable in the first slice, and then you can increment in the second slice. You can do it that way, or you can combine the two into one step and increment the program counter in the first step too. Now, doing it in the same slice can potentially end up with a race condition because it depends on who gets updated first. Okay, if the program counter updates really fast, but the ALU is really slow, you might end up using the wrong location to feed the ALU. So to play it safe, break it up into 2 steps. Okay, but if you put it into one single step, I'm not going to take any points off because we are not that concerned about race conditions in this class, but it can potentially happen. So PCEN, if PCEN is off, okay, if we separate it into 2 slices, then PC mux can be anything, because if PCEN is not enabled, then no path to the program counter is going to work anyway, so PC mux is irrelevant. Address mux is important because address mux is controlling what is driving the address bus of RAM, and needs to be a 1 in order to connect the program counter to the address port of RAM. So address mux has to be a 1. ALU OP has to specify the operation. A 0, 0, 0 in binary is what we want because that specifies an add operation. ALU EN has to be a 1 to enable the ALU. We are no longer using register output 1, so the demux of that particular port of the register bank can be anything. Doesn't really matter what it is. Actually, I take it back. I think the demux controls the enabling. Yep, it controls the, no, this is the selection. Yep, this is just a selection. It can be anything because we are not using it. So RO1 and RO1 demux and cell, they can be anything. It's irrelevant. RO0 demux can also be, no, this one is important. You have to keep it the same way as before. So you look at the add instruction, the current add instruction, it has to be the same thing because the first operand is still coming out of the register bank. So RO0 demux, which is this one here, RO0 demux, which is this signal, will still have to be the same, which means it still needs to be a 1 in this case in order to connect out 1 of your register bank to in 1 of ALU. So that one still has to be a 1. Okay. RO0 cell would now depend on which register we are talking about. Okay. So this is where you use XX. Because depending on which register we are specifying in the mnemonics, this can be 00 to specify register A, can be 01 to specify register B, 10 to specify register C, and then 11 to specify register D. Okay, you can either use XX or you can just specify this specifies the register. Just let me know that this is variable depending on which register we're dealing with. Okay, or you can just say assuming we're dealing with register A, this is going to be 00, but you have to tell me why it is 00. Okay. The next one is RO0 EN. We want that, okay, because we want this demux to be enabled. RI cell needs to be a 1, needs to be the same as RO0 cell because we are updating the same register. So this one still needs to be a 1. RIEN has to be a 1 because we are updating that same register after the operation. RI mux, let me see. RI mux is this one, so we want the mux to connect to the output of the ALU. So it needs to be a 1. So RI mux needs to be a 1, and the RAM load needs to be a 1 because we are reading from RAM. RAM cell needs to be a 1 because we are addressing RAM. IREN, or instruction register enabled, needs to be a 0 because we are not decoding a new instruction. And that specifies everything that you need to specify with one slice of microcode. Is that okay? Most of that you can just copy it from the existing add instruction. You just have to change, the several fields that you need to modify to get it to work with the new instruction. Is that okay? Yep.
What was the ALU again?
Huh?
Do that, it didn't matter for
No,
ALU?
it does matter because ALU op has to be 0, 0, 0 in binary to specify the add instruction. The 001 specifies subtract, 002 specifies, I think, and.
You click on, expand the
ALU.
circuit, you'll see where each.
Yeah, so in order to be well prepared for the test, don't count on me giving you the diagrams. You might want to print the diagrams yourselves so that you know that you have a copy. And then you can also blow it up to whatever size you want. That's the nice thing of having your own diagram. You can annotate it, you can add your own comments and whatnot. So I would definitely suggest that you bring your own diagrams. You can also color code it. You can just color code all the important lines just so that you can trace all those lines a little quicker. So you can do all kinds of stuff when you bring it up. Okay, so assuming that the first slice does not increment the program counter, we need a second slice to do it. So what do you think the second slice is going to look like? In terms of microcode pointer reset, should we reset it? Not yet, okay, because we need to clock it once so that the program counter is incremented. Okay, so we are separating the increment from the previous one. So we needed to increment. We don't want microcode pointer reset. This one still needs to be a 1 because we need to increment to the next microcode slice from this one. PCEN would now be a 1. It is important to turn it on now because we are going to update it. PCMux needs to specify something in order for PCMux to be enabled. And in order for it to choose the right path, which is incrementing. So because it's incrementing, we just have to make sure it's a 0. So PCMux, okay, is over here. So PCMux can be either a 5 or a 6, a 101 or a 110. Yeah, it can be one of those two. So the PCMux is going to be a 0 for incrementing, and the PCEnc is guaranteed to be a 1 also because of that. So PCMux can be a 5 or a 6. Address mux can be anything because this particular step does not use RAM because we are just internally incrementing the program counter. So address mux can be whatever it needs to be, whatever the value is okay. ALU op can be anything because we are not using the ALU. ALUEN should be disabled. RO1 demux can be anything, we are not using it. Cell can be anything, we are not using it. RO0, we are not using it, so the demux can be anything. This one can be anything. This one should be off, okay, because we are not using the register bank output at all. We are not using the input either, so RIEN should be a 0. RI cell can be anything because if the EN is a 0, it doesn't really matter what you use for the selection. RI mux can be anything because we are not updating anything as far as the register bank is concerned. RAM load can be anything because we are not using RAM at all. RAM cell has to be a 0 because you don't want to accidentally do something to RAM. And then IREN should be a 0 because we're not decoding any instruction. So that would be the second slice if you want to separate the two steps into two different slices. If you want to combine them into one single slice, you can do that just by merging the two slices, but it can lead to a race condition. Yep.
Would you need like a third slice to do the microcode pointer reset then?
That one is optional because I know everybody, know that that's gonna be the last slice, so it would not be required. All right. So there's that. And then the floating point number calculation is the next one. Did anyone actually work on it? Nobody. Okay. You can just kind of plug in these numbers into the code that I gave you guys, and then just watch it execute in GDB. Then you can get all of these answers, right?
We spent like what, 4 lectures or 5 lectures to do that homework for the floating points, so we sort of remember it. I mean, we have to, most of us do. I hope
Well,
so.
it takes a lot more effort to put a car together, but once you learn how to drive a car, it doesn't take you several weeks to drive the car again, right? All right, so let's go ahead and do question number 5, and then we'll go back and do the homework. Okay, the homework that was due on Thursday. Okay, step 1. So I'll follow exactly the same format. So step 1, assuming which number do you want to deal with? You guys get to pick which one.
The other one was that.
But there are 2 other ones.
Oh.
One is 1.28E2, and the other one is negative 7.8125E negative 2.
This is
That
that
one
one.
too, so.
That
Crazy
one?
yeah.
The crazy one?
Yeah.
Okay. Well, it's
It's
not as crazy as you think. Okay. So step 1 is the sign. The sign is a negative 1. Okay, so you say sign is negative 1, and then you say base 10. Okay, I'm gonna use Mantissa 10 to represent the other one, just so I don't have to type as much. So it's gonna be 7.8125 is my original Mantissa, and then we have exponent in base 10, and that's gonna be negative 2 to begin with. Is that okay? Step 1. So now we move on to step 2. So in step 2, I want to adjust the base 10 exponent so that the base 10 mantissa is no longer something that has decimal points. It is just an unsigned integer. Okay. So sign is still the same thing. You don't have to repeat sign if it doesn't change at all. But mantissa does change. So mantissa is now 78125, which means I am multiplying the mantissa by 10,000, and I have to adjust for that by decreasing the exponent in base 10 by 4. So now it is minus 6, negative 6. Are we doing okay so far in step 2? So step 2, the key is I don't want to change the value that is represented. I just want to change the components that I'm using to represent that value. Is that okay? All right. Okay. So now that this part is done, I go to step 3. Step 3. So step 3 is going to be the long one because it's a step-by-step process. So step 3 is going to have multiple steps all by itself. The sign doesn't change. You don't even have to say that, okay? Because once you identify the sign as negative 1 in step 1, that's fine, okay? No need to worry about the sign until step 6. Okay, so step 3 is going to be broken up into multiple steps because each step is I want to change the base 10 exponent 1 step closer to 0 in each step. Okay? So in this case, because my exponent in base 10 is negative 6, to get it closer to 0, I have to add 1 to it, right? To add 1 to ext10 means I have to subtract 10 from the mantissa in order to preserve the value. Right? Yeah, divided.
I think it's divided by 10 too.
Yeah, divided by 10, so that it's 1/10 of what it is now. Okay. So we'll go ahead and do that. So man 10, but we don't want to get into fractions. Okay, so we want to multiply the whole thing by 2, as much as we can, and then we divide it by multiply by 2, and then we divide it by 10. So we say, let's multiply by 2 first and see if a division by 10 is going to have any remainder. Because if it doesn't have any remainder, then we are cool. It's only when it has a remainder that we have to multiply by 2 as much as possible before we do a division by 10. Does that make sense? Okay. So we'll do it by multiply by 2 first, And even without a calculator, you can probably do this relatively quickly. Okay, so it's going to be what? 125. The other one is 156. 156,250, right? Looks like it. Okay, so EXP10 is still going to be, well, we can do the division by 10 here. Division by 10. Okay, we'll do it really step by step. Okay, my mind is working slow today. Okay, because I just multiplied this by 2, that means, if I track an exponent in base 2, that has to be a -1. Because this multiplied by 2 has to be countered by a subtract 1 of the exponent of 2. Is that okay? And then we can just go ahead and do the subtraction now. So I can combine those steps. Subtraction by 2 takes this 0 away, and then we're adding 1 to this. Is that okay? That's the first sub-step. So then we look at this number and go like, are we done? Is EXP10 or the 10 exponent a 0? Nope, not yet. So what we do is we do the same thing. So we look at 15625, and we say if we divide this by 10, we have a remainder. We don't like remainders. We would like the remainder to be a 0. So we say, let's multiply this by 2, but every time we multiply the mantissa by 2, we have to subtract the exponent of 2 by 1. And this becomes 3. Slow today, 31250. And then we look at this number and say, hey, this number is a multiple of 10. We can just go ahead and divide it by 10 without losing any precision. So we go ahead and divide this by 10, take away this 0, and increment EXP10 by 1. So it goes from -5 to -4. Is that okay? Right? And obviously that equality doesn't hold. So look at this, we go like, we're not done yet because EXP10 is still non-zero. So we say, okay, let's multiply this by 2. Remember, counter that by subtracting 1 from the 2's exponent. And we get this one to 6250. And then we look at this number and say, hey, that is a multiple of 10. We can just divide this by 10 clean without multiplying by 2 to make up for lost precision. So we say, let's take out that and increment this. Are we still doing okay so far? Next step, copy and paste. Look at this number, go like, if I divide this by 10, we will have a remainder of 5. Let's see what happens when we multiply this by 2. But if you multiply here by 2, you have to subtract 1 from EXP2. And this one turns out to be 1250, which is divisible by 10. Then we go ahead and divide it by 10, and we close the gap between EXP10 and 0. So we only have 2 more steps to go. Multiply this by 2, it is 250. Remember to subtract 1 from EXP2, add 1 to base 10. Get rid of the 0. And we're 1 step away. There we go. Multiply this by 2, subtract 1 from EXP2, and add 1 to EXP10, because this is going to be 50. 50 divided by 10 is going to be 5. So this is our final result in step 3. Are there any questions about this part? How would you check whether this is still the same value or not? What do you do?
5 by 2 to the negative 6 power.
Yep, exactly. Which is 5 divided by 64, right? So you look at 5 divided by 64 and you say, are we getting the same number back in base 10? If you are getting the same value back, then you did not make a mistake in the process. If If you're not getting the same value, then you have to kind of trace it back and go like, okay, where did I make a mistake? Typically, if you get it like twice as big, that means you forgot to make some adjustments to the exponent of 2. So there are certain errors that will lead to certain clear signs of problems. If it's 10 times more than what it should be, then you forgot to divide by 10 somewhere. Okay. All right. So now that we are done with step 3, we move on to step 4. Step 4, has the sign base 2 mantissa as an unsigned number. We have no base 10 exponent and some kind of base 2 exponent. So by the end of step 3, you have step 4 already. So we are now ready to move on to step 5. Step 5, says we want to implicitly shift the base 2 mantissa, so it looks like 1 point blah 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 in base 2. The base 10 exponent should remain as 0, but we also want to shift the base 2 exponent to handle the implicit shift. Okay. So now we have to look at the mantissa. So mantissa 10 is now the mantissa 2. So mantissa 2 is going to be the binary representation of 5, which is, what is 5 in base 2? 1, 0, 1, very good. Okay, so 1, 0, 1. So we'll start with this. Everything the same as before, except for man 10 is now man 2. In binary is 1, 0, 1. Okay. So you can either do it in one single step, or you can do it in multiple steps. Because if you want to do it in multiple steps, the implicit point is here to begin with. Okay. If you want to do it really, huh?
Let's do multiple steps.
Multiple steps?
Yeah.
Okay. So the first one is to move this point over here. And you're dividing the mantissa by 2, which means you have to adjust your exponent by adding 1. So it's going from negative 5 to negative 6. Excuse me, negative 6 to negative 5. Does that make any sense? Okay. So now you look at this and go like, we are not done yet because it's supposed to look like 1 point la 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 la. So we have to do it one more time. Move this point to here. And this is by dividing the mantissa by 2. But because you're dividing the mantissa by 2, you have to add 1 to the exponent to adjust for that. So this will be the final step in step 5. We now have 1.01 with a whole bunch of zeros to the right hand side. Those are all implicit. Times 2 to the power of negative 4. Are we still doing okay so far? Okay. So now that we are done with step 5, we move on to step 6. Step 6 is over here. Step 6 means we want to encode everything in the IEEE double precision file format. So you have to kind of remember where each component is. Okay. Now, if you cannot remember, you can always use your open note and bring that with you. Okay. So I can barely remember that. Okay. The sign bit is bit 63. The exponent is bit 62 down to bit 52. And then the mantissa, or the fraction part of the mantissa, is from bit 51 to bit 0. Okay, so I think that's how it breaks up into the various components. So we know the sign is going to be a 1. Okay, the exponent is the tricky one because the exponent is offset by 1023. If negative 4 is the value that you want to represent, you want to add 1023 to negative 4 to get to the actual number that you want to represent. So that means we are looking at 1023 minus 4, which is 1019, I think. Is that right? Okay. So we want to represent 1019, which is a base 10 number, as a binary number. Without a calculator, how do you do that? There's a quick way to do it. Okay? Since it's minus 4 is really, really easy. Yep, go ahead.
We find a number that is close to the power of 2, and so we go from there.
Yes. And what about 1023? So 1023 is extremely handy. 1024 is a power of 2, but 1023 is what? As a binary number, what does 1023 look like? It's 1 0 and then 11 ones. 10 ones, sorry. 10 ones. So we're looking at 0 and then 10 ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so this is 1023 in base 2. We don't want exactly 1023, we want 1019 or 1019 in base 10, which means we have to somehow get rid of a 4. Where's the 4? Let's see. This is a 1, this is a 2, this is a 4. How do we get rid of this 4?
0.
Turn it into a 0. Very good. There.
Or we can do binary subtraction.
Or you can do binary subtraction. Yep. But I'm doing this without a calculator. I'm just trying to show you guys how to do this kind of math without a calculator.
What did you do just now?
Huh?
What did you do just now?
I just took this 1 and turned it into a 0 because that's the same thing as subtracting 4 from 1023, which is what I need to do because the exponent part of a double precision floating point number is offset by 1023. Okay. So now we just copy that stuff here. Okay, 0, 1, 1, 1, 1, 1, 1, and let's see, 0, 1, 1, 1, 1, 1, 1, 0, 1, 1. Okay. And then the rest would be the fractional part of the mantissa, which means this part is never really represented in a double precision floating point number. That part is implicit. This part, on the other hand, is represented. We have a problem because we only got 2 bits here. This is far from 64 bits. What do? Pad it, okay? Just pad a whole bunch of zeros. La 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 la. That.
Can we pad it like that too?
You can pad it like that too, because the answer is, the question is asking you to give me the hexadecimal number representation. Yep.
I had a question before. I was writing down what you did up there, but I didn't hear you say. You were talking about like how can you check or something like that.
Right.
I forgot what it was. That was right.
I was, you can cross-check everything by hand all the way down to this step. Okay, so at this step here, how do we cross-check it? The mantissa in base 2 is really specifying 1 plus 0 of 1/2, right? Plus 1 of 1/4. So you're looking at 1 and 1.25, and then the whole thing times 2 to the power of -4. And then you have to, if you have a calculator, you can just calculate, is that the same value that we started off with? So even up to this point, you can still double check to make sure that your conversion process is correct. Yep.
Did you say if you have a calculator?
If you have a calculator.
Are we allowed to have calculators on
Yeah,
the exam?
you can have a scientific calculator. Yeah, you cannot have a calculator powerful enough to run logic sim or GDB.
Can you scroll down a little bit, please?
Mhm.
Just to see the final.
So, putting on the answer would be 1081.
Hmm?
So 0100 should be 0101.
Which part?
On the right.
Say,
The last four on the right.
you mean here?
Yeah,
There's no, the first one's not there.
because it's 1.01.
The one's implicit.
So we-
But the
okay.
yeah, the 1 point is implicit. We only use the fractional part.
Yeah.
Okay, so when you convert this into hexadecimal numbers, it becomes 1011 is one chunk. That is a B because it's 11, and then 1111 is F. 1011 again is another B, and then we have 4, and then you just have to pad zeros all the way so that you end up with 16 hexadecimal digits. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. There we go. That should be it. Is that okay? So basically, I just ran that algorithm sort of, by hand, taking a little bit of a shortcut because if I do not have a remainder in the division by 10, I can just go ahead and divide it. The whole point of making it as big as possible before you do a division is when you have a remainder, then that becomes useful.
What do you do again when you have a remainder?
If you have a remainder in a division by 10, then you want to make the numerator, which is your mantissa 10, as big as possible before you actually carry out the division by 10. So to minimize the accuracy loss.
Multiply by 2.
Multiply by 2 as much as you can, and before you divide it by 10. You multiply by 2 as much as possible before you divide it by 10. Because otherwise you end up with a significant loss of precision.
But it doesn't have to be a zero, right? Remainder zero. You
If
just
it
have to
has-
get it big enough so that the remainder is
Right.
close to zero.
Right, if it has no remainder, when you divide it by 10, you can just go ahead and divide it by 10. Because you're not losing any precision.
But if there is a remainder, then you just multiply it until you get
You get to the
minimal.
largest base 2 number.
But you're not gonna make us do that, are you?
Yeah, convert 1 point, there's some numbers that are not possible to represent, like if I give you like 0.3 to represent in base 2, you guys would go crazy because, you know, because it's recurring. You have to figure out which part is recurring at least to repeat that pattern. Yep.
Except for the positive, you multiply by 10 and divide by 2, right?
You do the opposite, which means you are going to multiply by 10 and divide by 2. Yep. And all the numbers that I use here as examples, they're all easy to deal with. Because 128 by itself is a power of 2, so it's pretty easy to deal with. And then the other one, which is 0.625, is 5/8, which is also easy to deal with. It's easier than this one that we just worked on.
Can you give us some more easy numbers to practice at home?
Okay, make
Come up
yourself
with
a
some-
random number generator.
But it should be nice. It should be nice. It should not be 0.3, right?
Okay, how about this? I'll give you a spreadsheet, or you can copy that later on, okay? But I'm not gonna, save it.
And if it has a representation in hexadecimal, we won't be great, so we can compare,
Okay, so if you want all the easy values to deal with, okay, so this is how you do it. Let me go to examples. So remember, go to the examples, subfolder, and I'm making this spreadsheet to give you something to chew on, okay? So you go to here, kind of rename it as floating point exercise. There we go. Okay, so it depends on how you want to do it. If you just want to do the, okay, I'll do it step by step. So we want to look at, okay, division. I'm trying to figure out the name to this, to use this one here. Units, okay, there we go. Units is good. So we want to basically use a negative power of 2 as our quote-unquote basic units. So we first figure out a negative number. So we want to use a random number between. And just to make it slightly challenging, we can make it from -2 down to -4 is already a 64, so we'll choose somewhere in between here. Doesn't like negative numbers in rand. Okay, fine, that's easy to fix. Just do the negation out, and then change all of these to positive. There we go. Okay, so your basic unit is now power 2 to this thing here. Okay. What?
Sorry, we're talking about 430.
440?
Data structures.
Oh, data structures? Okay. So units, and then you have quantities. So quantity is just going to be something that you can specify as a random number. So go ahead and just specify rand between, you can crank up the difficulty, you can crank it down, you can do anything in between. So I'm just going to pick something from 5 all the way to 100. Okay, doesn't matter. And then the value that you want to convert is just going to be quantity times units. There you go. Instant example, exercise generator. So convert 2.40625 into a floating point number representation. It's guaranteed to be relatively easy, okay? And I can also tell you, you know, how many digits, up to how many digits it's gonna take. When you look at quantity, it can only be up to 100, which means, you know, it only has 7 significant digits. Because 7 bits will get you 127 already, right? So that's basically as significant as it gets. What about units then? What about, you know, the -5, you know, that's controlling the power of 2? That's only changing the exponent. In other words, this part, row 1, is only affecting the exponent of the floating point number. It's only changing that part. If this number is really small, if it, instead of -5, if it's -20, it's just changing the EXP. It won't change the mantissa. The mantissa, or how difficult the mantissa can be, depends only on quantity, which at this point can only be up to 7 significant digits. Okay, if you don't want to deal with 7 significant digits, change that. Okay, you know, instead of making the random number all the way up to 100, crank it up only up to 50, 32, or something like that. Okay, and then the value is the actual number that you're converting. So you can tweak this in many different ways to kind of, you know, exercise, you know, it a little bit. How do you test that generated, you know, binary bit pattern to see whether it is actually representing 2.4065 or not?
I think we have homework that does it, right? We can run that homework program that we wrote.
Yep. All you need is a really simple program and GBB. Remember the trick that I did in GBB? And also the homework assignment, you know, also had a clue to do it using unions. So you can either use unions or you can use a typecasting the pointer to get to that. So once you have the hexadecimal representation of the binary representation of the double precision floating point number format, then you can store that into a 64-bit integer, take the address of that thing, cast the address to the address of a double, and then dereference that address. Then you can see whether the same value is printed or not. I know that's a mouthful, but that's the whole point of recording the lecture. So you just replay those 4 seconds a few times, and they're like, okay, write it down, step by step. Is that okay? So far so good, or? Okay, so I know we are running out of time for the lecture. I'm just gonna use the next 5 minutes or so to do the homework. Because remember on Tuesday, we have the homework assignments due. So let me just kind of use 10 minutes to work on the homework, and then we'll transition to the lab. If you want to go to the lab and study and just kind of work on all of these things, you know, in the lab, that's good. Okay, so we'll just go ahead and work on the homework assignment, which is in the previous section. Here we go. Nope, this one. There we go. Okay, so in the homework assignment, you're supposed to change the jump instructions into a jump I instruction so that it's very similar to what we just did today, okay? Except the processor is already modified, so you don't have to deal with that part. So I'm just going to use this to deal with that, okay? So let's see. I will implement 2 instructions and then test those 2 and then call it a day, because you know if it works with JCI and the JMPI, the rest should be okay. Okay, so we'll copy JMP. We already have a JMPI, so JMPI, and it is already done.
Yeah, we did it on Tuesday.
We did it on Tuesday?
Yeah.
Oh, okay.
Did you do the whole thing or just JMPI?
The other ones are pretty much the same kind of change. So let me take a quick look here. Vim JMPI, and what is the other one? Did we do another one like JLI? Yeah, JLI is here. I just want to make sure that they are done. Yep, it's done.
Okay, we did it all. Okay.
Yep. All right, cool. That was a quick one. But today I explained, you know, the rationale, you know, of how to approach the modification of the architecture itself. You know, how do you start with like, okay, there are these instructions permanently using this connection, and we don't want to affect those instructions. So you look for common attributes of those instructions, and then you look at the new instruction that you want to implement and go like, what about the new instruction? What lines will be exercised? How are they different? And then use that to help you control the MUPs to steer it one way or the other. So that's the basic rationale for that, how to change the MUP, how to modify the architecture. Okay, any questions before we make a transition to the lab? No questions? So your exam is on the Tuesday, because on Thursday we have the exam for 4:40. So I still have office hours on Thursday after the break, tomorrow, as well as the Monday after the break. So we have 3 potential office hours before the exam. So if you have any questions about the material, you'll go ahead and use the office hours. And also the lab time, I'm gonna keep the lab today.
Wait, so what was your office hours again?
My office hours are, let me switch to here, just so that it is, it's included in the, so tomorrow, which is Friday, it is from 8 o'clock to 9 o'clock. On the Monday after the break, it is also 8 o'clock to 9 o'clock. And then on the Tuesday, it is right before the class before this one, which is 3:30 to 5:30. All right, any other questions? Okay, so to most of you, have a nice break, and for those of you who are going to the lab, I'll see you over at the lab.
I was triggered as soon as I saw it.
And let's hope, I
Your
did
brain
turn
just
on the
shut off?
recorder. Yep, I did turn on the recorder.